This is the part 2. This is the problem number 3, which is the same as the problem number 2 from the practice test. And it's simple, the problem. Electrical power is typically stated in units of watt. So 1 watt is going to be equal of 1 joules per second, because that's the way the unit was set up. About 95%, 90.0%, 95.0% of the power output of a bulb is converted to heat, and 5% to light. And what do we care? The heat of the light. In this case, we care about the light. Why? Because we'll read the problem. Because if a 10% of that light, do you see, is at 5% of the total watts or joules per second, it's a 5%, and then it's a 10% of that light shines on your chemistry textbook. How many photons? They're asking for the photons. Again, per second. Wow. And you see it's not too difficult. Shine on the book from 100 watts bulb. And then they're giving it also the wavelength of 550 nanometer, which is the UV, um, the visible spectrum. So the wavelength is down here. It's gonna be equal to 550 nanometer. As we know, we're gonna be using meter. Let's convert it. So it's gonna be, and I'm gonna leave it like that, 550 by 10 to the minus 9 meter. Now here, again we know, right, that the energy, if we divide the energy, okay, coming from the bulb, which is would be the total on the chemistry book, divided by the energy of photons. Because remember, the photons are the smallest particle, the microscopical. The light that shines on your book is the total, and it gives me the number of photons on that light that it's shining on the book. So how do we calculate each one? Well, in one way, we can calculate the energy of a photon. How? Well, we have the wavelength again. So it's kind of the same thing that we're doing. And it's the h 6.626 by 10 to the minus 34. That's our h. Multiply. Again, we have wavelength of 550 by 10 to the minus 9. And wavelength would be equal wavelength by, I'm sorry, let me start it again. C is equal to wavelength multiplied by the frequency. So in this, you know that the energy is the of a photon would be the Planck by the frequency. So what you have to do is energy equals h multiplied by what? By the speed of light divided by the wavelength. You find out, or you can either find out the frequency first, right, by dividing the speed of light by the wavelength that you have it, 500 nanometers, and then the value, you plug it in this equation, or we can use this as I'm doing during this video. So this is going to be 10 to the 8 meter per second, second and second cancel out, divided by 550, right? By 10 to the minus 9. Look at the bottom on the left. 10 to the minus 9 meter. So meter and meter cancel out. So the energy of a photon with an um, wavelength of 550 nanometer would be 3.6 by 10 to the minus 19 joules per photon. So now let's find out the total energy that of the light that shines on our textbook. I'm looking at this, right? Let's look at this for a second. The total energy would be equal to what? You got 100 watt, but 100 watt is the same as 100 joule per second. Yes or no? Yes. And that's how you'll see. That's why we can calculate the photons per second, because the energy we got is 100 joules per second. So if we divide to calculate the number of photons, right, is the total energy divided by the energy of a photon. This total energy is given in joules per second. So, because it's the energy from the bulb in watt. So that way we can calculate the energy, the number of photons per second. Let me do it. Let me do it and we'll see it better. So we got this. Now we know that only from that 100 joules per second, of energy, we only gonna have 95, right? 95, 5%, which is 0.012, okay, of light, and at 10%, which is zero point 0.1, okay, on the textbook. 5% would be the light, and 10% of that light is the one that is going to shine on the book. And that's what they're asking for. They're asking for at the light that shines on your textbook. So it's per second that shine on the book. So it's a 5%, a 10% of a 5% of 100 watts. So you multiply this 100 joules per second by 0.05 by zero 0.01, and it gives you 0.5 joules per second. And that is the light from the bulb that shines on the textbook. Now, how many photons per second? Well, to calculate the number of photons per second, we divide photons per second. We divide the energy here, 0.5 joules per second, divided by the energy of a photon, which is going to be 3.6 by 10 to the minus 19 joules per photon. And this would give us the photons in the units of photons per seconds. That's what I'm saying. And this is going to be 1.388, 1.39 by 10 to the 18. And this would be, wait, and this is going to be photons per seconds. That's the answer for this. Now let's do the next one. Okay, this is a little bit longer, but basically what we have to do is an important reaction is the conversion of natural gas to other useful hydrocarbon to other useful hydrocarbons is the conversion of methane to ethane. In practice, this reaction is carried out. Oxygen, I think something is missing on there. But the idea is that the conversion of from methane to ethane is an important useful conversion. And this reaction is carried out at industrial grade, right? Industrial, um, in practice, industrially, it is carried out in the presence of oxygen, which converts the hydrogen produced to water. So what is the difference of here? Here you produce hydrogen, right? And but here with oxygen you convert this hydrogen to water because you have the oxygen here. So what does it say? Calculate the delta H for the two and then compare them. Why is the conversion of methane to ethane more favorable when oxygen is used? Let's do both. Let's start with the letter A and let's do the letter B. So the first thing when you do this equation, I do recommend you to do the bonds like that. I don't know if I probably give it to you in the exam, which it saves you time too. So we got this gas, right, gives me you got one more of C H H H. I'm doing a kind of a Lewis structure here, but I'm writing the formula. You got one of this, and then you got one hydrogen, and this is gas, and then you got hydrogen, gas, gas. So what do we do here? Well, what we have to do in the letter A, let's start with the letter A. We're going to do the enthalpy of the bond broken plus the enthalpy of the bond formed, which is a negative. By the way, I got a mistake here. And this is typing. This is hydrogen. Okay, I forgot to put the other one. So now let's start with that. Where do we get this energy? Well, I'll give you the table on the exam and you can find it on your book, but there's a table here. So we start by multiplying by 2 moles because we have two molecules CH4. So it's 2 moles, right? Oops. 2 moles of how many CH bonds you're breaking? 4. Okay, so let's look for the value of CH bond energy. So here it is, it's 413 kilojoules per mole. So it's 413 kilojoules per mole. And this is the same table you're going to have on the exam. Okay, so let's do the right side. On the right side, we got only 1 mole, okay, of 1, 2, 3, 4, 5, 6, 6 CH, okay, which is the same. The CH bond, the energy for the CH is 413. The only difference is that this negative, but it's 6 times because now we're forming 6 CH bonds. Then we got, again, we got 1 mole but we have here, you can add them together and multiply, but I like to do it in separate. You got 1 mole of a CC bond, so it's 1 CC bond, right? So it's 1 multiply, what is the value for the CC energy? And it's negative because we're forming a CC bond that we didn't have here. So it would be, CC would be 347. Minus 347 kilojoules per mole. And then the formation of a hydrogen-hydrogen bond, which we got 1 mole, and hydrogen-hydrogen bond would be 432. So it's negative, and we got only 1 per mole. So do your adding and subtracting, okay? So it's gonna be here, it's gonna be, I think it's right, 3,304, which is 8 by 4, 8 by 4, 4, okay, 2 by 4, 8, yeah, it should be right. Kilojoules, right? Plus, and this is gonna be a negative because it's 1 by 6 by minus. So it's gonna be minus 2,478 kilojoules. And then minus here, 101, 347 kilojoules minus 432 kilojoules. All this, right, is going to give you the value, the delta H of this reaction is going to be 47 kilojoules. Very little energy you need, but you need energy. If we do the part B, right, the part B is the CH4 again, and we only have 1 mole. We have half a mole of oxygen gas, 1 of ethane, and 2 molecules of water. So we would have 1 plus half a mole of, which is 1. It's a way of representing this, but it's the same. This is gas. This is gas. So we produce here 1 of ethane, mm, plus 2 of water. And the water is 2 OH bonds. So it's going to be 2. So here we got, I'm going to put the values directly. We got here 4 of the hydrogen. So it's going to be 4, 1 mole, 1 mole, 4, 4, 1, 13 kilojoules per mole, which cancels out. Okay, plus 1.5 moles. Multiply. Now be careful here with the one you use, because if you look at the table, you have the one for O2, and that's a special bond energy. Every time you have O2 gas, O2 oxygen, O2 gas is 498. Oh, okay, 799 in CO2 is 498. Okay, so here would be 498 kilojoules per mole, and we have only half a molecule. And then plus again would be the same as the other one. We have 6 of the CH, so it's gonna be 1 mole, 1 mole multiply by 6 because we have 6CH, right? 6 multiply by the CH, which is going to be minus because we're forming the CH bond, kilojoules per joule per mole, sorry. And this plus, now let's go to the water, but no, let's go to the formation of the of 1 mole because we got one of the CC bond. And remember, the energy was 347 for that one. So, and it's only one, so it's minus 347 7 kilojoules per mole. And finally, with the water, which is making a big difference here because it's plus 2 moles, but you're multiplying it by twice because we have two OH bonds that are forming, and it's gonna be 2 by minus 467 kilojoules per mole. Now it does make a difference with the one we had before. So doing all this operation, I just gonna write down the results. You can double check. So here it's gonna be 1,000, 1,652 kilojoules plus 249. You see how little energy it takes to break the oxygen, to add oxygen. You have to add only a little bit. But you have to, you're going to release a lot of energy forming these bonds. Because if you look at this, this is the values. This stays the same, which is the minus the CC bond, right? But now let's take a look at the water, which is minus, right? And this water is 4 by for that, it's going to give me my 1,868 kilojoules. Just check the answers, and if you see something, it's 1,060.52 plus 249 minus 2,040.78 minus 347 minus 1,086.8. I double checked it, but it gave me minus 2.792 kilojoules. Now, if you compare this for the reaction B using oxygen with the one we got without the oxygen, you can see right away that this needs a little bit of energy, and this is releasing a lot more energy, meaning that this is spontaneous, and that is what it favors, the formation of ethane from methane using oxygen is releasing energy and is spontaneous.